It begins in the quiet hum of a backyard, under a blanket of stars most of us never truly see. The air is cool, the equipment is familiar, the routine is practiced. An amateur astronomer named Rai points his telescope not at some famous nebula or well-known planet, but at a faint, speeding dot designated 3I Atlas, the latest interstellar visitor to grace our cosmic neighborhood. He captures his frames, stacks them, and begins the tedious process of sharpening, standard procedure for anyone trying to tease detail from the deep dark. But this time, something in the data pushes back. This time, the noise resolves not into chaos, but into order. An order so precise, so eerily geometric, that it feels less like a discovery and more like a message. 5 points of light. Not a random scattering, not a smudge or a streak. 5 distinct bright nodes arranged in a rough but undeniable circle around the comet's fuzzy core. It's a pattern that stops you cold, the kind of symmetry that triggers a primal alarm in the back of your brain. Symmetry means intelligence. Patterns mean design. And this pattern, circling an object born around another star, looks too perfect to ignore. Rai's setup wasn't exotic. An 8 to 14-inch Schmidt-Cassegrain telescope, a standard RGB sensor, the kind of gear thousands of dedicated hobbyists have in their garages and backyards. This wasn't the Hubble Space Telescope. It was something far more powerful and relatable, curiosity made manifest in commercially available optics. He wasn't using specialized filters for infrared or ultraviolet, just the standard tools to capture reflected sunlight from this distant traveler. When he began stacking those multiple exposures, a process designed to reduce noise and bring out faint signals, the 5 points emerged from the void. They weren't glaringly obvious in the raw data, just whispers at the edge of perception. But the stacking algorithm, a tool that reinforces consistent features, latched onto them, and they persisted. This wasn't a single-frame glitch. Across multiple captures, separated by minutes, the formation held. If these were just hot pixels or sensor noise, they would flicker in and out of existence randomly. Instead, they remained coherent. They stayed in formation, a silent, coordinated ballet around a comet millions of miles away. The immediate reaction, from scientists and online communities alike, was a scramble for mundane explanations. Diffraction is the usual suspect. Light bending around the edges of telescope optics can create spikes and rings and patterns. Every astronomer knows this. It's the fingerprint of your instrument on the sky. But diffraction patterns shift as the telescope tracks. They change shape with the angle of incoming light. Rai's 5 points did not. They held their positions, roughly equidistant, a stable configuration around a moving, outgassing object. The next suspect was background stars. Maybe Rai's tracking was slightly off, and faint stars had smeared into arcs that just happened to fall around the comet in a misleading way. But the timescale doesn't work. His exposures were short, and stars don't behave like that. They are points or slight streaks, and they drift in straight lines across the field of view. They don't appear to circle a central object. They don't maintain a perfect, shifting formation. And then there's the footage itself, the sequence of events that transforms a strange, still image into a dynamic mystery. Rai didn't just capture one moment, he captured several sequences over about 30 to 40 minutes. And in those sequences, the 5 points shift. Not dramatically, not in a way that screams obvious orbital mechanics, but they change position relative to each other and to the comet's core. In one frame, they are in one configuration. 6 minutes later, they have rotated slightly. A few minutes after that, they have shifted again. If you were to watch this happen in real time, you would swear something was moving. Something was circling. This is the detail that separates a curious anomaly from a genuine enigma. Persistence implies structure. It implies something holding those bright regions in place against the natural, dissipating forces of space. The public reaction was a digital firestorm. The phrase, "too perfect to be random," echoed across forums and social media platforms. People started calling them escorts. Some suggested autonomous probes, a swarm of intelligent sensors travelling with the comet. Others went further, proposing that 3I Atlas itself wasn't a natural comet at all, but a vehicle, a generation ship, or a probe masquerading as one. The speculation spiral had begun. But underneath the noise, a legitimate question began to form, a question that even careful, skeptical scientists were starting to ask in the privacy of their own minds. What configuration of natural processes produces this pattern? Why does it look so much like something maintaining a perimeter? This is where our journey starts, not with a conclusion, but with a single, breathtaking image that shouldn't exist. We're going to walk through every frame, every anomaly, every impossible detail that makes this the strangest interstellar visitor we have ever seen. Because something is moving around that comet, and we need to figure out what it is before it's gone, back into the interstellar void from whence it came. If you're feeling what I'm feeling right now, that pull toward the unanswered question, that thrill of the unknown, then you're in the right place. I want you to be part of this investigation every step of the way. So, hit that subscribe button and ring the bell. You won't want to miss a single development. And let me know in the comments right now, where are you watching from? What time is it there? I want to get a sense of this community, spread across the globe, all of us looking up at the same time, wondering about the same strange lights in the darkness. The story is just beginning. The professional response, however, was a study in caution. Optical scientists are split. One camp looks at RISE images and sees exactly what you'd expect from dust jets combined with aggressive, imperfect processing. Comets are messy. They eject material unevenly. A rotating nucleus with active vents can produce bright clumps of dust that scatter sunlight, and from certain angles, those clumps can appear to surround the nucleus. Add sharpening algorithms that exaggerate edges, and you can easily create the illusion of geometry. Artifact cluster, they call it. Nothing to see here. But others aren't so sure. The spacing bothers them. Even with generous assumptions about projection effects and dust dynamics, getting 5 roughly equidistant bright nodes is statistically weird. Not impossible, but weird. And the minute scale evolution bothers them even more. Because if these are just dust clumps in the coma, they should disperse. The coma is an expanding cloud. Material doesn't orbit, it flows outward, pushed by solar radiation and the comet's own outgassing. Anything in the coma should be drifting, spreading, dissipating. But RISE 5 points remain coherent across tens of minutes. They shift, yes, but they don't dissolve. They don't blur into the background haze. This persistence is the heart of the mystery. It's the thread we will pull on, a thread that will lead us into rotations that defy logic, into jet geometry that breaks the rules, and into a silence from the world's leading space agency that is, itself, louder than any press conference. This is just the beginning. The 5 points are the key. Now we have to see what door they unlock. Comets spin. This is a fundamental truth, as basic as their icy composition. They are irregular chunks of primordial ice and rock, tumbling through the vacuum, heated unevenly by the distant sun. As frozen volatiles vaporize, jets act like tiny, misaligned rocket engines, pushing asymmetrically on the nucleus, inducing a rotation or changing its characteristics over time. Most comets are slow, stately tumblers, their periods measured in hours or even days. Studying them is a patient, methodical art, tracking subtle changes in brightness and coma structure over weeks to build a picture of their orientation and spin. Which is why what Rye observed in less than 2 hours is so profoundly disruptive to that established rhythm. Because 3i Atlas doesn't just appear to be spinning, it appears to be spinning fast, uncomfortably fast, and the nature of that spin doesn't just bend the rules, it seems to be playing an entirely different game. It started subtly, during Rye's review of his captures. The comet's coma, that fuzzy, ethereal cloud of gas and dust, wasn't a static, glowing blob. Over remarkably short intervals of just 60 to 90 seconds, the density distribution within the coma was shifting. Brighter regions, presumably areas of more intense outgassing, would rotate around the central core. Fainter areas would emerge as others faded. It created an effect not unlike watching a lighthouse beam sweep across a foggy night. The source is stable, but the visible manifestation of its energy moves in a predictable, repeating arc. Except in this case, the comet itself seemed to be the rotating source, and the beams were jets of material erupting from its hidden surface. This was the first clue that something was off, a visual hiccup that separated Atlas from the thousands of other comets humanity has observed. Here is where the analysis becomes a labyrinth of mirrors, both literal and figurative. Rye's camera setup, like most in astrophotography, can introduce image flips depending on the optical path. A diagonal mirror or certain types of correctors can flip the image horizontally or vertically. So when Rye pored over his sequences, the rotation appeared clockwise in some frames and counterclockwise in others. This on its own is entirely normal and expected. But when you correct for all these known instrumental effects, when you digitally untangle the optics and track the actual motion of features in the coma against the fixed background of stars, a stubborn and puzzling pattern emerges. The object is rotating with a surprisingly short period, potentially on the order of just minutes. For a comet nucleus estimated to be several kilometers across, this is not just unusual, it is borderline physically implausible. The structural integrity of these icy rubble piles is weak. The forces generated by rapid rotation would easily overcome the meager gravity and chemical bonds holding the nucleus together. A comet spinning with a period of a few minutes would be under enormous centrifugal stress, likely tearing itself apart. While not entirely impossible, especially for a smaller, unusually cohesive object, it immediately raises alarm bells. The evidence for this rapid spin is etched into the sequence of frames. Frame 20 shows the bright core with a slight asymmetry, a jet or a surface feature pointing in one distinct direction. Frame 14, captured approximately 6 minutes later, shows that same asymmetry rotated by a significant margin, roughly 30 degrees. Frame 9 shows it shifted again. When you map these angular changes onto a rotation curve, the math points to a period somewhere between 15 and 25 minutes. This is fast enough to be deeply unsettling, but perhaps it isn't a pure, simple rotation. Perhaps the object is precessing. Imagine a top spinning on a table, its axis slowly tracing a circle as it wobbles. This is precession, a complex motion where the spin axis itself rotates. Comets can precess, especially when they are outgassing asymmetrically. The jets provide torque, acting like tiny thrusters that push the nucleus off balance, inducing wobbles and tumbles. If 3I/Atlas is precessing rapidly, that could explain the minute scale changes Rye observed. It could also explain why the changes possess a certain stability, a rhythm that seems too structured to be random chaos. Precession has its own periodicity, and periodicity can look intentional even when it is a purely natural, if complex, physical phenomenon. Crimson is another, more conventional force at play, rotational wobble driven by outgassing torque. This is a well-documented phenomenon. When material jets off a comet, it carries away momentum. If the jets are active predominantly on one side of the nucleus, they create a torque that can spin it up or alter its spin rate. The Rosetta mission witnessed this firsthand with Comet 67P, watching its rotation period change slowly over months. But 3I/Atlas seems to be exhibiting changes on a scale of minutes, not months. This implies either an astonishingly powerful and dynamic outgassing process, something far more violent than we've seen before, or another, unknown force is affecting its motion. Or, of course, it could all be a grand illusion. The skeptic's refuge lies in the concept of imperfect tracking. If Rye's telescope wasn't perfectly locked onto the comet's motion across the sky, the coma could drift slightly within the frame, and features would shift position. When you stack these subtly drifting images, you can create the illusion of rotation where none exists, an effect known as field rotation. It's a common pitfall. Except Rye's starfield doesn't show the same drift. The background stars remain crisp points, their positions consistent from frame to frame. If field rotation were the culprit, the stars would be streaked or show the same apparent motion. They don't. This single observation punches a significant hole in the simplest artifact-based explanation. It is this very stability, this rhythmic and persistent motion, that caught the attention of the wider world and, inevitably, the conspiracy theorists. Because if 3I/Atlas is rotating rapidly, and if that rotation is stable and controlled rather than chaotic, it starts to resemble something deeply familiar to human technology: a spacecraft. Satellites and probes use spin stabilization for attitude control. They are designed to maintain orientation. The rotation Rai observed looks, to a pattern-seeking brain, like something maintaining control. Now, it is crucial to state clearly, there is no evidence of artificiality, none. But the pattern, the feeling of it, invites the comparison. And once that seed is planted in the cultural consciousness, it becomes nearly impossible to uproot. Physics, of course, offers other escape hatches from this puzzle. One is frame aliasing, the well-known wagon wheel effect. If you're sampling a rotating object at intervals that aren't perfectly synchronized with its rotation period, you can perceive a reversal or a stuttering in the motion. It's an illusion created by the discrete nature of the sampling, but it is a convincing one. Could Rai's exposure spacing have created such an artifact, making a slower rotation appear faster or even reversed? It's possible, a variable that must be meticulously checked. Then there is the critical question of how this rotation, real or illusory, connects to the 5-point anomaly. If both features are genuine, they might be intrinsically linked. Imagine a nucleus with 5 active vents spaced evenly around its equator. As it rotates, each vent fires in sequence, creating bright pulses of dust that, from our distant vantage point, appear as persistent points maintaining their position. This is a clean, natural explanation that fits within known physics. But it circles back to the same nagging problem. It requires an almost perfect arrangement of vents. It brings us back to the question of symmetry. Why is it so symmetric? Why does it look so meticulously arranged? NASA has not commented on any rotation parameters for 3I/Atlas. No official spin period, no analysis of precession or wobble has been released. This silence is conspicuous. Usually data flows freely and quickly. With Atlas, the faucet has been turned to a drip. Perhaps they are being thorough, checking and rechecking. Or perhaps they are seeing the same bewildering data that Rai captured and are struggling to build a model that explains it without igniting a media firestorm. We are left with a comet that spins too fast, too smoothly, with features that shift in ways both regular and strange. We are left with questions about torque and wobble, and whether any of it connects to those 5 silent sentinels. And we are left to wonder if the rotation is the key to understanding the anomaly, or merely another layer of confusion piled upon an already baffling object. Comets are messy. This is the first and most important lesson in cometary science. They are not pristine, smooth spheres governed by orderly processes. They are jagged, irregular, and pockmarked bodies, shaped by billions of years of accretion, collision, and cosmic weathering. They are coated in dusty lag deposits and riddled with volatile pockets that heat unevenly as they fall toward the sun. When those ices vaporize, they do not erupt in a uniform geyser. They blast out from localized vents and fractures, creating asymmetric twisting jets that spiral and evolve as the nucleus rotates. The result is a beautiful, dynamic chaos. No 2 comets look alike, and no single comet looks the same from one week to the next. So, when you are presented with images of a comet exhibiting a repeating, symmetric structure in its coma, your first instinct must be profound skepticism. Because nature, for all its wonders, does not do clean, geometric symmetry. Not like this. Not usually. To understand why 3I Atlas is so confounding, we must first look at its interstellar predecessors. The first, 1I Oumuamua, was an enigma of minimalism. It barely outgassed at all. It showed a non-gravitational acceleration, a tiny push that couldn't be explained by gravity alone, suggesting some kind of material release. Yet it left no visible coma, no tail, no obvious trail. It moved like something was pushing it, yet it was optically inert, a dark, reddish bullet. The second, 2I Borisov, was the polar opposite. It was a textbook comet in many ways: strong activity, a bright and expansive coma, clear evidence of carbon monoxide outgassing, and jets that shifted and flickered chaotically as it tumbled through the inner solar system. It was asymmetric, unpredictable, exactly what scientists expected. Neither of them showed anything remotely resembling the 5-point formation Rai captured. Neither of them looked coordinated. Atlas, however, sits in a strange middle ground. Like Borisov, it is clearly active, with a visible coma, but like Oumuamua, it possesses features that defy standard models. It's as if it took the strangeness of both its predecessors and combined them into something entirely new. RISE footage shows something beyond just 5 bright points. When you enhance the contrast and trace the faint radial streamers of dust within the coma, you see patterns that align with these bright nodes. It looks for all the world like multiple jets firing simultaneously, each one creating a bright region where dust scatters sunlight most efficiently. But herein lies the core of the geometric problem. The simultaneous activation of 5 equidistant jets is not something that occurs naturally. Comets do not have evenly spaced vents. Their surface geology is random, a product of stochastic processes over eons. Finding 5 active regions spaced precisely 72 degrees apart is statistically so unlikely that it forces you to question the assumption itself. It's not impossible, but it sits so far out on the bell curve of probability that it demands rigorous scrutiny. There are, of course, scientific avenues to explore. One compelling idea is that of axis-aligned dust vents combined with a projection effect. If the comet's rotation axis is oriented in just the right way relative to both the Sun and Earth, and if there are vents clustered near the equator, they could activate in sequence as the nucleus turns. From our specific, privileged perspective, this sequential firing could create the illusion of all 5 jets being active at once. It's akin to the constant beam of a lighthouse. The bulb only points in one direction at a time, but to an observer, the beam appears as a continuous sweep. This explanation is mathematically sound and fits within known physics, but it requires a very specific, almost contrived alignment of geometry and perspective. The coincidences begin to pile up. Another hypothesis involves resonant structural features within the nucleus itself. Imagine an object with internal cracks or layering shaped by eons of thermal stress cycles. As it heats up, these pre-existing weaknesses could channel gas in predictable, repeating directions, creating organized patterns in the coma. Some asteroids exhibit similar resonant behaviors, their spin rates locking into states that produce symmetric features. If 3I Atlas has an internal structure that promotes this kind of resonance, the jets could appear organized without any artificial influence, simply following natural pathways carved by its unique geology. Again, this is possible, but again, it requires a set of very specific initial conditions. Then we have the shadowing, a detail that adds another layer of deep complexity. In several of RISE frames, there are dark ridges visible within the coma. These are not just dim regions, they are pronounced dark areas, as if something solid is blocking the light from the nucleus. Shadows imply structure. They require an object with enough density and definition to cast a silhouette. In a diffuse, glowing cloud of gas and dust, you do not expect sharp shadows. The material is too tenuous. Everything should glow and scatter light softly. But if there is a more rigid underlying shape, a fractured nucleus with large, distinct lobes, those lobes could rotate and create shadow zones within their own coma. The Rosetta mission saw this dramatically on Comet 67P. Its rubber duck shape cast deep, complex shadows across its own surface. 3I Atlas could be similar, a bizarrely shaped object casting moving shadows as it spins. This would neatly explain the presence and shifting nature of the dark ridges. Except, the shadows in RISE images don't behave quite right. They shift, yes, but they also seem to be correlated with the bright points. Where there is a bright node, there is often a corresponding dark ridge nearby, as if the two features are linked. This is harder to explain with simple shadowing from a central nucleus. It suggests some kind of organized structure within the coma itself. Perhaps dense dust lanes, regions where material has clumped together, creating both bright reflections from their sun-facing sides and dark gaps in their lee. We cannot ignore the spectre of processing artifacts. The heavy sharpening that Rai applied to bring out faint details is a double-edged sword. Sharpening algorithms work by enhancing edges, increasing the contrast between adjacent pixels. This can create dark halos or overshoot around bright objects, artificially mimicking shadows where none exist. It is a well-known pitfall in image processing. Yet when analysts go back to RISE's less processed stacks, the shadows are still there, fainter and less distinct, but present. They are not purely a product of the sharpening. They are a persistent feature, and their persistence is what gives them weight. The act of stacking itself amplifies radial symmetry. This is a fundamental and often overlooked fact of astronomical image processing. When you overlay multiple images of an object that has any rotational component, patterns that repeat, even weakly, will be reinforced. Random noise averages out, but consistent features get brighter and more defined. It is like applying a filter that inherently prefers order over chaos. And humans, looking at the result, will instinctively latch on to that order. We are wired for pattern recognition. We see faces in clouds, constellations in random stars, and design in noise. So a significant possibility remains that RISE images are primarily revealing our own cognitive biases, showing us what we want to see rather than what is truly there. But what if the nucleus itself is the source of the symmetry? Some asteroids are faceted, their shapes honed by collisions into vaguely geometric forms. If 3I Atlas is a fractured body with flat faces and sharp edges, its rotation could create repeating patterns as different facets point toward the Sun. Each face would heat differently, activating different sets of vents, producing jets that appear in a symmetric arrangement. A tumbling cylinder or elongated shard could produce a similar periodic effect. Or perhaps it is a binary or even a multiple system, several bodies orbiting a common center of mass, each contributing to the coma and creating a pattern that looks, from a distance, like a single object with escorts. This would explain a great deal, but there is no evidence for it in the orbital data. No periodic brightness variations from mutual eclipses, no gravitational wobble in its trajectory. This relentless push and pull between natural explanation and anomalous observation is the essence of the Atlas mystery. The speculative angle that continually resurfaces is the question of engineering. Could the shape be non-random? Could those 5 jets be something akin to nozzles? Could the rotation be controlled? It sounds like science fiction, until you remember that humanity has already sent precisely such objects beyond the solar system. Voyager, Pioneer, New Horizons, probes that maintain orientation using thrusters and spin stabilization. If we can do it, the reasoning goes, why couldn't another intelligence? It is pure, unsubstantiated speculation. There is no evidence. But the geometry, the stubborn, repeating symmetry, keeps inviting the question. Why does it look so designed? And why, when we try to explain it with natural processes, do we find ourselves needing a cascade of special conditions, perfect alignments, and convenient coincidences? The answers are not in the grand claims, but in the tiny details. The next clues are hidden in the data itself, in the metadata RI didn't notice, in the anomalies buried beneath the layers of processing and assumption. Every astronomical image is a palimpsest, a document with layers of information. The pretty picture of a galaxy or nebula is just the surface layer, the final rendering. Beneath it, embedded in the digital file itself, is a second narrative, written in the cold, precise language of data. Exposure times, sensor temperatures, timestamps, tracking coordinates. And buried deeper still, in the relationships between pixels and across sequences of frames, are clues that can distinguish a revolutionary discovery from a compelling artifact. RISE images of 3I Atlas are no different. On the surface, they tell a story of 5 bright points and strange rotation. But in the metadata, in the details he didn't highlight and likely never even noticed, there are whispers of something even stranger. This is not proof, not yet, but it is a collection of hints. And sometimes, hints are more profoundly unsettling than answers. Blackmail the first of these subtle clues lies in the star streaks. In astrophotography, a telescope must track the sky to compensate for Earth's rotation, keeping the target centered. Perfect tracking yields pinprick stars. Imperfect tracking smears them into short, straight lines. This is normal. RISE images show these streaks, as expected, but upon meticulous inspection, some of these streaks are not straight. They are bent. Not dramatically, not in a way that screams a catastrophic error, but with a slight, consistent curvature, as if the tracking speed changed mid-exposure, or as if the stars themselves moved in gentle arcs rather than straight lines. This should not happen. Stars move with a constant linear motion relative to a tracking telescope. If the tracking is off, the streaks should be straight, just angled incorrectly. Curved streaks suggest a non-uniformity in the tracking, a serious mechanical fault, or, more intriguingly, micro-movements of the object being tracked that are inconsistent with predictable comet motion. A comet's path is a smooth curve governed by gravity, with tiny perturbations from outgassing that act over days or weeks. They do not cause sudden jerks or oscillations. If 3I Atlas were wobbling or shifting its position rapidly enough to impose this curvature on the background stars, it would imply forces acting upon it that are not in any standard model. Solar radiation pressure is too weak. Outgassing torque would need to be impossibly strong. Gravitational interactions are ruled out. There is nothing of significant mass nearby. Yet the star streaks curve, and this anomaly is a quiet, data-driven problem that can't be explained away by image processing. Congressional definitely. RI the color gradients. RI's RGB sensor captures light in red, green, and blue channels, which are combined to create a full color image. Comets typically show soft, blended color variations based on dust composition and grain size, often reddish near the nucleus where larger particles dominate, fading to bluer tones further out where smaller grains scatter sunlight more effectively. What is not expected are sharp, distinct color zones. RI's images, however, show exactly that. Patches within the coma with saturated, distinct colors that seem wrong for a simple RGB setup observing reflected sunlight. They look almost like emission lines, the kind produced by specific fluorescing gases, but RI wasn't using narrowband filters designed to isolate such emissions. So where are these colors coming from? The immediate suspect is sensor noise. At high ISO settings or lung exposures, digital sensors can produce artifacts. Hot pixels glow, cold pixels drop out, and the demosaicing algorithms that interpolate color can create false gradients. If RI's sensor was noisy and his processing amplified it, these color zones could be entirely artificial. But noise tends to be random, grainy, and chaotic. These color patches have structure. They align with the bright points and follow the larger geometry of the coma, suggesting they are not pure noise. They are responding to something real in the image. This opens the door to other possibilities. Dust with an unusual mineral composition, contamination in the optical path, or, most intriguingly, something in the coma genuinely emitting or reflecting light in ways we don't expect from a typical comet. RI's stacking strategy itself is a critical piece of the puzzle. He didn't just average his frames, he cropped them tightly around the comet, aligned them with precision, and applied variable levels of sharpening. Light sharpening for overall structure, heavy sharpening for faint details. Then he adjusted contrast curves, brightening the dim regions and compressing the bright ones to fit a viewable dynamic range. Every single step is standard, defensible, and commonly used by amateurs, but every step also introduces risk. Sharpening can turn faint sensor noise into apparent structure. Contrast adjustments can make random fluctuations look like coherent features. Tiny alignment errors can create ghost images that seem to orbit the target. Stacking is a powerful tool, but in the pursuit of an aesthetically pleasing image, it can forensically compromise the data. RI, like most enthusiasts, was focused on clarity and detail, not on preserving the data for courtroom-level scrutiny. 3 frames in particular have attracted focused attention from those who have dissected the data. They show what appear to be fireball-like tails trailing the object. These are not the smooth, diffuse tail of a comet, but discrete, almost clumpy structures extending behind the nucleus. Some researchers suggest this could be jet backflow, material ejected sunward that gets caught by the solar wind and swept back into the tail. Others point to dust clumping, a process where particles collide and stick together, forming larger aggregates that reflect more light. Both phenomena are possible and have been observed in other comets, but they are typically chaotic and disorganized. The tails in RI's images look too linear, too organized, as if something is being deliberately dragged behind the object rather than naturally dispersing. The concept of oscillatory motion is another key to understanding the potential illusions at play. If 3i Atlas is rocking or yawing, nodding its axis back and forth as it rotates, that motion would create repeating patterns in stacked images. Features would appear to pulse or shift rhythmically. Over multiple frames, this rhythm would build up, creating what looks like solid structure, even if the object itself is fundamentally chaotic. Spacecraft experience this. Imperfect attitude control leads to a periodic wobble visible in telemetry. For a comet, the same principle applies if outgassing creates an uneven torque. The nucleus rocks, the jets sweep back and forth, and from a distance, the entire system can appear to have an internal order. It is an illusion born from repetition, but it is a convincing one. Professionals who have reviewed RISE footage have used a telling phrase, consistency in inconsistency. What they mean is that the anomalies are not random. The bright points don't flicker arbitrarily. The color zones don't shift chaotically. The curved star streaks don't appear in random frames. There is a pattern to the weirdness, and patterns suggest underlying causes. Whether those causes are artifacts of imaging and processing or real physical phenomena is still unknown. But the fact that the strangeness repeats, that it has a structure, means it is not just noise, it is a signal. The monumental question is, a signal of what? The history of amateur astronomy is littered with cautionary tales. Hot pixels can cluster deceptively, lens flares can appear in formation, diffraction spikes can align in misleading ways. Every experienced imager has been fooled at least once by something that looked real, but was merely a trick of the light and silicon. Skepticism is not just warranted, it is essential. But so is curiosity. Because if the micro-shifts in RISE data are real, if the object genuinely wobbled, or if material is moving in ways not explained by standard comet physics, then we are looking at something extraordinary. Mass redistribution, jet torque far stronger than expected, or, in the most speculative of scenarios, something controlling its motion. The metadata doesn't provide answers, but it frames the questions with a terrifying precision. There is a rhythm to discovery in the modern age, a predictable cadence of observation, analysis, and announcement. A new object is spotted. Telescopes are tasked. Data is collected, preliminarily analysed, and summarised in a press release or briefing. The process, from first light to public statement, typically takes days, perhaps a week for complex data. The message is clear. We are looking, we are on it, science is in motion. It is a ritual of reassurance, a way to tell the public that the experts are in control, that the universe, however vast, is being monitored and understood. So when that rhythm breaks, when the most prominent space agency in the world goes silent, people notice. And they start asking why. RISE footage achieved viral escape velocity almost instantly. Within 48 hours of his initial post, it was a global phenomenon. Within 72, mainstream science outlets were covering the story. A global network of amateur astronomers began pointing their own telescopes at 3i Atlas, attempting to replicate the observation. Some saw hints of the pattern, others saw nothing. This inconsistency fueled the debate, but the one voice everyone expected to hear was conspicuously absent: NASA's. No tweet, no blog post, not even a holding statement saying, "We're aware of the footage and are investigating." Just silence. In an era of instant communication, this silence feels heavy, deliberate, and loaded. Can contrast with previous interstellar visitors is stark. When Oumuamua was discovered in 2017, NASA released data within days: orbital parameters, size estimates, reflectivity measurements. When Borisov arrived in 2019, the response was similarly prompt and transparent. The public felt included in the process of discovery. With 3i Atlas, the pattern has been broken. The object was detected, its interstellar trajectory confirmed, and then a curtain of quiet fell. A scheduled briefing was announced, then postponed, then rescheduled, and postponed again. Officials cite ongoing analysis and data calibration, the standard lexicon of delay. But these excuses feel hollow when amateurs with backyard equipment are producing and sharing compelling images in real time, and the agency with the most powerful telescopes ever built has, apparently, nothing to show for itself. This void has inevitably been filled with rumours. Unconfirmed chatter, purportedly from individuals connected to the Jet Propulsion Laboratory or the Space Telescope Science Institute, whispers of early Hubble data stacks showing structural anomalies in the coma. They speak of features that shouldn't be there, patterns that match rise captures, but with the crystal clarity of a space-based observatory. These rumours are specific. They mention image processing pipelines flagging geometric structures, internal emails debating how to classify certain observations, and meetings where scientists argue over how to present findings without triggering a frenzy of speculation about artificiality. There is no smoking gun, no leaked classified image, but the persistence and specificity of these rumours are themselves a social phenomenon of note, a symptom of the tension created by the official silence. It is crucial to understand that NASA operates under policies that generally mandate public access to publicly funded data. But these policies have caveats. Data can be withheld temporarily if a premature release might compromise scientific integrity, if there is a high risk of public misinterpretation or alarm over something that may turn out to be entirely mundane. The agency can choose to take its time, to ensure that when it does speak, its statements are bulletproof. The problem is that delay creates a vacuum, and a vacuum is the natural habitat of speculation. Every day of silence makes the conspiracies a little stronger, the questions a little sharper, and the public trust erodes a little more. There are, of course, perfectly rational and defensible reasons for the delay. Processing data from faint, distant objects is a monumentally complex task. Raw images from space telescopes are flooded with noise, cosmic rays, scattered light, instrumental artifacts. Calibrating this data, subtracting backgrounds, registering frames, and stacking them properly is a painstaking process. Rushing it risks releasing dramatic-looking images that are, in fact, just noise amplified by poor processing. NASA has been burned before by rushed releases. The agency is determined to be slow and right rather than fast and wrong. This reasoning is impeccable until you consider that Rai, with consumer-grade equipment and software, produced a compelling result in a weekend. If he can do it, why can't NASA in 2 weeks? The answer lies in the rigour of multi-wavelength confirmation. Professional astronomers don't rely on visible light alone. They want infrared data from JWST to measure thermal emissions from dust. They want ultraviolet data to detect gas fluorescence. They want spectroscopic data to identify specific molecules. They want to coordinate observations from Hubble, ground-based observatories with adaptive optics, and any other available asset. Synthesizing this multifaceted dataset into a coherent picture takes time. It is not laziness, it is the very essence of scientific thoroughness. The critical question hangs on this synthesis. Do the 5 bright points Rai captured show up in the infrared? If they do, they are real, physical structures emitting heat. If they don't, they are likely optical illusions, artifacts of reflected visible light. This distinction is the difference between a monumental discovery and an embarrassing false alarm. Withdrawing, the automated pipelines that process space telescope data are inherently conservative. They are designed to filter out anything that looks anomalous, classifying it as a potential artifact to be removed from the final clean image. If 3i Atlas has faint structures that register as anomalous to these algorithms, they might be systematically stripped out. Scientists would then need to manually dive into the terabyte-sized raw data archives, identify what was removed, and determine its validity. This process is not quick. It involves comparisons, simulations, and consultations. To the public, it looks like stonewalling. To the scientists, it is simply diligence. Disregarding the list of NASA's likely concerns is the ghost of Oumuamua. That object sparked a years-long debate that saw a respected Harvard astronomer seriously propose an artificial light sail, leading to a media circus that NASA then had to spend months carefully navigating. The agency knows that interstellar objects trigger outsized reactions. If 3i Atlas shows even a hint of strangeness, they will be asked point blank, is it artificial? They will face immense pressure to comment on the escort hypothesis. Every statement will be dissected, every image analysed by millions of armchair experts. It is a public relations minefield. So, they delay. They triple-check. They prepare their messaging. They try to control the narrative before it controls them. The internal debate at NASA is likely a tense one. One faction argues for immediate transparency. Release the data, even if incomplete. Acknowledge the uncertainties. Let the global scientific community help. Another faction argues for extreme caution. Do not feed the speculation. Wait until we have definitive answers. Do not give conspiracy theorists ammunition. Both positions are defensible. The tension between scientific openness and institutional risk aversion is real, structural, and not malicious. But from the outside, it looks an awful lot like they are hiding something. The clock, however, is ticking. 3i Atlas is moving away from the sun, getting dimmer with each passing day. Every week, it becomes harder to observe. The window for obtaining high-quality data is closing. NASA knows this. The question haunting everyone is, are they seeing the same 5-point pattern? If Hubble or JWST images show a smooth, asymmetric coma, the mystery collapses and RISE footage becomes a cautionary tale. But if their images show the same pattern, clearer and more defined, then the game changes entirely. The conversation shifts from, is it real? To, what is it? And that is a conversation for which no one, not even NASA, may yet have an answer. Kang, let's play a game. Let's assume, for the next several minutes, that Rai captured something unequivocally real, that the 5 bright points are not artifacts, not misinterpreted dust jets, not illusions of light and processing. Let's assume they are actual, discrete objects or structures, maintaining position relative to the comet's nucleus as it spins and travels through the void. This is a monumental assumption, likely a wrong one, but assumptions are the tools of exploration. They allow us to map the territory of possibility. They force us to ask, if this were true, what would it look like? What physics would it require? What configurations make sense? And most crucially, what future observations could prove or disprove it? So let's explore the escort hypothesis not as believers, but as investigators. Let's see where the idea leads, and whether it holds up under the harsh light of physical scrutiny. Consider the purely geological possibilities. Comets fragment, tidal forces from a close stellar pass, internal thermal stress from approaching a sun, or rotational breakup from spinning too fast. All of these can shatter a nucleus into multiple pieces. If 3i Atlas fractured at some point in its deep past, those fragments might still be travelling together, held in a loose gravitational association. From a distance, you would see multiple bright points, each a smaller comet in its own right, contributing to a combined complex coma. The spacing would depend on the violence of the breakup and the subsequent gravitational interactions. But here lies the first major problem with this theory. Gravitational interactions between multiple fragments are not stable over long timescales. The pieces would drift apart, their orbits evolving, or they would collide. Maintaining 5 fragments in a stable ring-like configuration for the millions of years it likely took Atlas to reach our solar system requires impossibly precise initial conditions. It's possible, but statistically, it's a lottery win. Furthermore, fragments orbiting a central body would exhibit periodic brightness variations as they eclipse one another or present different phases to our view. We see no such periodic dimming or brightening in RISE data or any other observations. The 5 points maintain a relatively constant luminosity. This is a significant strike against the simple fragment hypothesis. What if the points aren't separate objects, but are instead fixed to the nucleus? Imagine a comet with 5 exceptionally active vents spaced evenly around its equator. As it approaches the sun, these vents heat up and erupt, each producing a brilliant plume of dust and gas. From our specific viewing angle, These plumes could appear as discrete points surrounding the nucleus. This is the most palatable natural explanation. It doesn't require anything exotic, just a very, very specially shaped comet. But it does require a cascade of specific conditions. The vents need to be at approximately 72-degree intervals. They need to activate simultaneously, or in such rapid succession that they all appear active within a single exposure. And the dust they eject must scatter light with peak efficiency directly toward Earth. That is a lot of ifs. The question then becomes, how does a comet nucleus acquire such a symmetric arrangement of vents? Random accretion over billions of years in a protoplanetary disk produces chaos, not order. Collisions shatter and randomize. So, if the vents are real and symmetric, something must have shaped the nucleus in a profoundly deliberate way. Even if that shaping was purely geological, the result is indistinguishable from design. This leads us to more exotic but still natural internal structures. A crystalline or lattice-like internal composition offers another angle. Some minerals and ices form in repeating geometric patterns. If the comet's interior is composed of, or contains large regions of, a crystalline material, thermal stress could cause it to fracture along those pre-existing crystalline planes. This would create symmetric weak points, guiding volatile escape and producing regular jet patterns. It's analogous to how a crystal of calcite cleaves into a perfect rhombohedron when struck. The internal order dictates the external form. Applied to a comet, an internal crystalline lattice could dictate where vents open, creating a symmetric outgassing pattern. This is plausible on small scales. Water ice crystals are hexagonal, for instance. But extending this to an entire kilometre-scale comet nucleus requires the body to have long-range crystalline order, which is unprecedented. Cometary nuclei are thought to be rubble piles, loosely bound aggregates of ice and rock, not single, giant crystals. Still, if 3I Atlas formed under unusually calm and slow conditions, perhaps in a dense, cold molecular cloud, such a structure isn't impossible. It's just wildly unexpected. Venturing further into speculative territory, we encounter plasma-based explanations. Plasmas, often called the fourth state of matter, can form complex structures. Magnetic fields can trap and organize charged particles into stable configurations that persist far longer than random gas would. In laboratory settings, physicists have created plasma knots, toroids, and filaments that exhibit remarkable stability. Could something similar be happening in the coma of 3I Atlas? If the comet is ejecting a significant amount of ionized material, and if there is a magnetic field present, either intrinsic to the comet or from its interaction with the solar wind, this plasma could self-organize into discrete, glowing nodes. These nodes would appear as bright points, and if the magnetic field geometry were just right, they could arrange themselves into a symmetric pattern. The challenge here is that comets are not known to be strongly magnetic. Their nuclei are not made of ferromagnetic materials. The solar wind provides a weak ambient magnetic field, but it is generally too disorganized at these distances to create such a perfect, stable ring. This explanation requires plasma physics at the very edge of our understanding of cometary environments. Even more speculative is the concept of photonic resonance. Light exerts force. Radiation pressure is a real, measurable phenomenon. In principle, if the dust particles in the coma were of a very specific size and composition, they could be pushed by sunlight into stable positions where radiation pressure balances the weak gravitational pull of the nucleus. These would be points of photonic resonance, places where the light from the sun creates standing waves in the dust distribution. The pattern would be geometry dependent and could, theoretically, produce a symmetric arrangement. This has been proposed for other astrophysical contexts, but never confirmed observationally. Applying it to 3I Atlas requires a fine-tuning of dust properties and solar interaction that seems, once again, highly unlikely. It also raises the question, if such resonances can occur, why have we never seen them in any of the thousands of other comets we've observed? Return to more concrete physics, orbital dynamics provides a tangible, if challenging, option. Small fragments from a prior breakup could be in orbit around the main nucleus. If the comet split violently, ejecting material at specific velocities, Some of that debris could have achieved a stable orbit. Orbital mechanics would then govern their motion, and depending on the mass distribution and rotation of the primary body, stable orbits could exist that would make the fragments appear as a ring from our perspective. This is real physics. We see it with moons and rings around planets. The problem, once more, is scale. Comet nuclei have incredibly weak gravity. To maintain a stable orbit, a fragment would have to be so close to the surface that it would be skimming the tops of the highest peaks. At that range, atmospheric drag from the comet's own expanding coma, even its tenuous coma, would cause rapid orbital decay. The fragments would spiral inward and collide with the nucleus within days, weeks, or months, not the years or millennia required for an interstellar journey. The configuration is inherently transient, unless the fragments are being continuously replenished, or the coma is far less dense than we assume. This brief tour of the escort hypothesis reveals a consistent theme. Natural explanations exist, but they all pile coincidence upon special condition upon statistical improbability. The hypothesis forces us to confront the limits of our knowledge about how matter behaves in extreme and unique environments. It doesn't prove artificiality, it simply highlights that a natural explanation would be, in its own right, a revolutionary discovery. It would mean that interstellar space contains objects with formations and properties we have never dreamed of. The escort hypothesis, as a thought experiment, succeeds not in proving aliens, but in proving that whatever 3I Atlas is, it is forcing us to expand our imagination of what is possible in the cosmos. You are looking at a two-dimensional image, a flat projection of a three-dimensional event occurring millions of miles away. A comet is spinning, perhaps precessing, and moving along its orbital path. Around it, 5 points of light seem to dance. The question is simple, but the answer is buried in layers of geometry. Are those points rotating with the comet, fixed to its surface like volcanoes, or are they moving around it, like moons in orbit? RISE images don't give us a Hollywood-style 3D model we can rotate with a mouse. We are stuck with a series of flat pictures. Yet, scientists have developed powerful techniques for teasing out motion from such limited data, and some of these methods can be applied even to amateur observations. The first technique is differential luminosity analysis. It sounds complex, but the principle is straightforward. By comparing the brightness of each of the 5 points across dozens of frames, you can begin to map how their illumination changes. If all 5 points brighten and dim in unison, it suggests they are all tied to the same phenomenon, likely fixed to the rotating nucleus, with their activity pulsing as different sides are heated by the sun. However, if they brighten independently, in a clear sequence, like lights chasing each other around a Christmas tree, then you might be looking at separate objects orbiting the nucleus, each catching the light as it swings around into view. RISE frames show something frustratingly in between. The points do not all pulse in perfect sync, but they also don't follow a clean, sequential pattern. It's messier, more organic. This could be the result of a tilted rotation axis relative to our line of sight, creating a complex interplay of illumination and shadow that obscures a simple pattern. It could also mean we are seeing a combination of effects, some fixed features and some orbiting ones, or a single structure with a complex geometry. Then there's coma backscatter analysis. The dust cloud itself is a diagnostic tool. When sunlight hits these tiny particles, a portion of that light is scattered directly back toward the source, in this case, roughly toward the sun, and, coincidentally, toward us. By analysing which parts of the coma are brightest, researchers can infer the orientation of the nucleus. If dust is being thrown off from a specific region on a spinning body, the backscatter pattern will shift in predictable ways as that region rotates in and out of sunlight. The subtle shifts in overall coma brightness in RISE images do suggest the object is rotating, but the speed of these shifts is the real shocker. They happen over timescales of 60 to 90 seconds. This implies either a terrifyingly fast rotation, which would be unprecedented for an object large enough to sustain such a coma, or a strong precession. Precession, the wobble of the rotation axis, can create illusions. A slowly rotating object that is also precessing wildly can appear to change its orientation much faster than its true rotation rate. It's the difference between a perfectly spinning top and one that's about to fall over tracing wild circles on the table. But here is where the escort hypothesis tightens its grip. If the 5 points are merely fixed to the surface, vents or craters, then as the nucleus rotates, we should see them move in predictable arcs. Their positions relative to each other should change dramatically. They should spread out, overlap, and reconfigure as the sphere turns. Instead, they maintain their spacing. They hold their formation. This persistence is the single most compelling argument that they might not be surface features. They could be something else entirely. Prohibitors have proposed they might be clumps of dust trapped in stable orbits, held in place by a delicate balance between the nucleus's weak gravity and the outward pressure of its own outgassing jets. This phenomenon, known as a Trojan or horseshoe orbit, can occur when particles get caught in gravitational sweet spots, oscillating around stable points without escaping or falling back. The math checks out. Small particles in a specific size range could, in theory, be suspended in quasi-stable orbits around an active comet. They would appear as bright points because they are reflecting sunlight, while the darker nucleus below provides contrast. And if the comet is rotating, these particles could maintain their relative positions if their orbital period is synchronized in some way with the spin. But there's a catch. For 5 separate dust clumps to arrange themselves into a symmetric ring and stay there requires either an astronomical coincidence or some organizing force. Gravity alone does not naturally create evenly spaced orbiting bodies. Look at the irregularity of asteroid moons. You would need another force, perhaps electrostatic forces from charged dust, or the magnetic field ideas we discussed earlier to enforce the symmetry. Scientists who specialize in comet rotation, like those who studied 67P Churyumov-Gerasimenko with the Rosetta mission, know how fiendishly complex spin states can be. 67P tumbled chaotically, its rotation axis wandering over time due to the uneven push of its jets. If 3I Atlas is doing something similar, its rotation could be changing even as we watch it, making any simple model useless. RISE data, with its limited resolution and short time coverage, cannot definitively answer the question of what the 5 points are, but it strongly suggests a system of baffling complexity. It hints at a level of structure far beyond a simple, spinning lump of ice. If we take the speculative leap and assume the points are in orbit, we can use the shifts between RISE frames to calculate a rough orbital period. The math suggests they would be completing one full orbit roughly every 3 to 5 minutes. This is, to put it mildly, insanely fast. At that speed, they would need to be orbiting extremely close to the nucleus, just a few dozen meters above the surface, or centrifugal force would instantly fling them into interstellar space. Could fragments orbit a comet that quickly? Perhaps, if the nucleus is far denser than we think and the fragments are mere pebbles. But it pushes against the very limits of plausibility. We are left with 2 equally staggering possibilities. We are looking at an extremely unusual and poorly understood natural configuration, or we are seeing something that our current physics struggles to describe until a space-based observatory with high-resolution capabilities tracks 3I Atlas for hours instead of minutes. This question will remain open. But the fact that a person in their backyard with commercially available gear brought us to the precipice of this question is a testament to the power of passionate curiosity. Professional astronomy is a leviathan. It involves telescopes the size of buildings, supercomputers running calibration algorithms refined over decades, and global teams of PhDs who have dedicated their lives to extracting truth from starlight. You would think that such a machine would miss nothing, that its systematic gaze would catch every detail. But history tells a different story. Time and again, it is the lone observer, the dedicated amateur in their backyard, who first lays eyes on the impossible. Consider March 1995. A comet named Hale-Bopp is cruising through the outer solar system, still more than a year from its dramatic close encounter with the Sun. Professional observatories are monitoring it, of course. Their images are fed through automated processing pipelines designed to produce clean, publishable data. These pipelines are programmed to remove anything that looks anomalous: cosmic ray hits, hot pixels, tracking errors. Anything that doesn't fit the expected profile of a smooth, symmetric coma is filtered out as noise. Then, an amateur astronomer in Texas, observing with his backyard telescope, notices something strange. The comet's nucleus isn't a single point. It appears doubled. There seems to be a second, smaller core trailing the main one. He posts his images online. Within days, other amateurs around the world confirm it. Hale-Bopp has a companion. It has fragmented. The professionals, alerted by the amateurs, go back to their own archived data. And there it is. The fragment is clearly visible. But their automated software had dutifully classified it as an artifact and removed it. The amateurs saw it first because they looked at the raw data with human eyes, with pattern recognition brains evolved to notice something that shouldn't be there. Or recall July 1994 and the epic collision of comet Shoemaker-Levy 9 with Jupiter. It was one of the most watched astronomical events in history. Every major professional telescope on Earth and in space was trained on the giant planet. They had the impact times calculated down to the minute. But in the days leading up to the impact, amateur images from across the globe began capturing something the big scopes had missed. Faint secondary fragments trailing the main string of pearls of the disintegrated comet. These pieces were too dim for the automated surveys to flag as significant, but they were visible to patient amateurs willing to stack dozens of long-exposure images by hand. These fragments turned out to be very real. Some of them struck Jupiter hours after the main impacts, creating secondary fireballs that no professional model had predicted. The amateurs didn't just watch the show, they helped rewrite the script. Then there's the spectacular ohms. In October 2007, this normally faint comet underwent a monstrous outburst, increasing its brightness by a factor of 1,000,000 almost overnight, becoming visible to the naked eye. Who captured the most detailed early images of the expanding debris cloud? Amateurs. They were the first to see the intricate structures within the outburst, radial jets, spiral patterns, and shells of material that suggested the nucleus was rotating and throwing off material in organized, if violent, streams. By the time the major professional observatories could be scheduled to point at Holmes, the initial, most dynamic phase of the outburst had already evolved. The amateurs owned the discovery of the event itself. Why does this keep happening? How do individuals with gear you can buy online repeatedly outpace billion-dollar facilities? Part of it is sheer coverage. There are thousands of amateur astronomers scattered across the globe, observing every clear night. They are not bound by telescope allocation committees, grant proposals, or peer review. If something interesting happens, they can simply point their scope and start collecting data, driven by nothing but raw curiosity. They are a distributed, global early warning system. But there's another, more subtle factor: processing. Professional data reduction pipelines are designed for scientific rigor. They employ aggressive noise reduction, flat field correction, and artifact removal. Their goal is to produce a clean, calibrated dataset for quantitative analysis. This is the correct approach for most science. The problem is that these pipelines are conservative. They are designed to throw out the junk, but sometimes the baby goes out with the bathwater. A real, faint, anomalous structure can look, to an algorithm, exactly like a sensor glitch. Amateurs, especially those processing their own images, often use gentler, more customizable techniques. They might use different stacking methods, apply moderate sharpening, and prioritize visual clarity over statistical purity. They are not trying to write a journal article, they are trying to see what's there. And sometimes, buried in the noise they choose to keep, is a signal that the professional pipelines would have erased. Rye's images of 3i Atlas fit this historical pattern perfectly. His stacking choices were unconventional by professional standards. He used tight cropping and selective sharpening instead of the heavy-handed noise suppression a standard pipeline would apply. This is precisely why the 5 points are so prominent in his images. A professional pipeline might have smoothed them into oblivion, classifying them as correlated noise or a sensor artifact. Does this mean they are real? Not necessarily. It simply means they are persistent enough to survive his particular processing choices, which is the first step toward being taken seriously. The inherent danger, of course, is that these same amateur techniques can also create compelling artifacts that don't actually exist. Rolling shutter effects, minor tracking errors, sensor blooming, and hot pixels that coincidentally line up across multiple frames can all conspire to create false structures that look bewilderingly organized. Professional processing exists specifically to guard against these false positives, so we are left in a state of tension. Amateurs see things professionals miss, but they also see things that aren't there. The key is replication and independent verification. In Rye's case, that verification is underway. Other amateurs are now training their telescopes on 3i Atlas. Some report seeing the 5 points, others see 4 or 6 or a smeared ring. The variation itself suggests that processing choices and atmospheric conditions are playing a huge role. But even if the 5-point formation ultimately fades under professional scrutiny, Rye's images have already achieved something of immense value. They have forced the entire astronomical community to look more carefully. They have prompted professionals to go back to their own data of 3i Atlas and check. Did we filter something out? Are we missing something? They have sparked a global conversation about what interstellar objects can be. This is the true legacy of amateur astronomy. It does not replace professional science, it provokes it. It asks different questions, looks at the data with fresh, unjaded eyes, and reminds the experts that the universe still holds surprises. And until NASA releases its own definitive images, Rye's footage remains the most detailed public window we have onto this mysterious visitor. For now, the amateurs are leading the charge, and the world holds its breath, waiting to see if they have found a fundamental truth or simply revealed how easily we can find patterns in the unknown. Let's talk about the elephant in the room. The online communities that are absolutely, fervently convinced that Rye's images are proof of an alien spacecraft, a mothership with a drone escort, a deliberate artifact of intelligence. They are wrong, almost certainly. The dramatic music, the red circles, the labels like escort craft and scout probe. It's a familiar and often cynical playbook. They take lens flares and call them force fields. They take sharpening halos and interpret them as energy shields. They rebrand color gradients from sensor noise as exotic propulsion signatures. If you don't understand how digital cameras and image processing work, it's easy to be swept away by the narrative. But if you dismiss them entirely, if you write them off as mere cranks, you risk missing a crucial point. Underneath the layers of unsupported speculation, they are noticing something that is genuinely strange. The 5-point formation is anomalous, even if it isn't alien. The even spacing of the points bothers everyone who looks at it with a critical eye, not just the conspiracy theorists. Diffraction patterns, a common source of optical artifacts, typically produce spikes or isometric blooms, crosses or 6-pointed stars. They do not, as a rule, create 5 distinct, evenly distributed points in a ring. It's an unusual configuration. Similarly, dust jets from a rotating comet can create multiple bright regions, but to have 5 of them, synchronized in their appearance and spaced at perfect 72-degree intervals, requires either a geological miracle on the surface of the nucleus or some other, broader organizing principle. The conspiracy theorists jump to intelligence as that principle, but the anomaly exists regardless of its cause. Then there's the flicker synchronization. Several analysts who have independently processed Rye's frame sequences have reported that the 5 points seem to brighten and dim in a loosely coordinated way. They don't all pulse in perfect unison, but their luminosity variations appear to be correlated, not random. This coordinated behavior is catnip for the artificial control crowd, but it's also exactly the kind of detail that suggests a real, underlying physical process is at work. It's a signal, not just visual noise. One potential natural explanation involves rotating dust structures. If the nucleus has a specific flattened or elongated shape and is spinning rapidly, it could throw off dust that forms temporary shell-like structures. As the nucleus rotates within this shell, different sections would catch the light at repeating intervals, creating the illusion of synchronized flashing across multiple points. It's speculative, but it's rooted in physics, not fantasy. monitored the long non-alien explanation involves electric fields. Comets moving through the solar wind can build up a significant electrical charge. This charge can, in turn, organize the surrounding dust. In laboratory experiments, charged dust particles have been shown to self-organize into filaments and surprisingly regular structures, condensing at specific distances from a central charged object. If 3I Atlas is highly electrically active, a possibility for an interstellar object moving at high relative velocity through the heliosphere, those electric fields could be sculpting the dust in its coma into the geometric pattern we seem to see. The conspiracy channels don't talk about electric fields or Trojan dust orbits. They leap directly to extraterrestrial surveillance. But their core observation, that the pattern looks organized, is not in itself an irrational one. Where the conspiracy theorists go fundamentally wrong is in their underlying assumption that structure implies intelligence. We are, as a species, hyper-specialized pattern recognition machines. We see a face in the craters of the moon, a pyramid in a Martian hill, a message in random radio static. Our brains evolved in a world where a rustle in the grass was more likely to be a predator than the wind. Assuming agency, assuming that an organized pattern means someone organized it, was a survival advantage. But this instinct becomes a liability when we turn it on the cosmos. The universe produces symmetry and structure constantly, effortlessly, and mindlessly. Snowflakes are hexagonal because of the geometry of water molecules. Saturn's rings are banded because of orbital resonances with its moons. Spiral galaxies wind their elegant arms through the action of gravity and density waves. None of these breathtaking structures required a designer. But when we see a new, unexpected symmetry, especially on an object from another star, our ancient brains scream, "Designer!" So the conspiracy theorists are wrong about the cause, but they are not wrong to point out the effect. The 5-point formation, if it is real and not a perfect storm of artifacts, represents something that does not slot neatly into our existing models of comet behavior. That strangeness is worth investigating. That strangeness is worth taking seriously. The problem is that taking it seriously involves the boring, unglamorous work of running simulations, testing hypotheses, comparing the data to other known comets, and waiting for better data from professional observatories. Conspiracy theorists lack the patience for this. They want an answer now, and they want it to be world-shattering. Scientists, on the other hand, are professionally comfortable with uncertainty. They know that the vast majority of anomalies turn out to have mundane explanations. They've seen too many revolutionary discoveries collapse under scrutiny. So they approach RISE images with a default skepticism, looking for the simplest explanation first. This caution is the bedrock of good science, but it can sometimes lead to the premature dismissal of a genuine, if less dramatic, discovery. The truth about 3I/Atlas likely lies in a messy middle ground. The 5 points are probably a combination of real features and processing artifacts. Some of what Rye captured is likely genuine cometary activity, real jets or dust concentrations that exist in the coma, and some of it is almost certainly enhancement and noise, amplified by stacking and sharpening until it looks more defined and geometric than it truly is. Separating these two components is the real challenge, and it requires data that amateurs simply cannot provide. We need the calibrated, multi-wavelength observations that only NASA or other space agencies can deliver. In the end, the conspiracy channels have performed one unintended service. They have kept the spotlight on the anomaly, they have generated public interest, and ensured that when NASA finally does break its silence, millions of people will be watching, waiting for an explanation. If there is anything unusual in the official data, the pressure on scientists to address it clearly and transparently will be immense. So yes, the conspiracy theorists are wrong about aliens, but they are asking a question that resonates with everyone who has seen RISE images. What is actually out there, and why does it look like that? Even if the ultimate answer is a complex but natural one, the question itself is valid. Because every now and then, just often enough to keep us humble and curious, the universe reveals something that truly shouldn't exist. And we won't know if 3I/Atlas is one of those moments until we look at it with the best tools we have. We have now been visited by 3 confirmed interstellar objects, 3 messengers from other star systems, each carrying the chemical and physical imprint of a world we will never see. They are our first tangible samples of galactic diversity, and if we line them up side by side, a pattern begins to emerge. Not a pattern that proves anything about intelligence, but a pattern that suggests we have been thinking about interstellar space in a dangerously narrow way. The cosmos is not just populated with familiar comets and asteroids that happen to be drifting. It is a gallery of the strange, the unique, and the unexplained. The first, One-Eye Oumuamua, discovered in October 2017, was an exercise in minimalism and mystery. Its name, meaning scout or messenger in Hawaiian, was eerily apt. It was already on its way out of the solar system when we found it, a dark, reddish object accelerating away from the sun. This was the first clue to its strangeness. It was accelerating slightly, more than gravity alone could explain. Comets do this through outgassing, the jet-like release of vaporized ices. But Oumuamua showed no visible coma, no tail, no evidence of activity whatsoever. It was too small and fast for detailed imaging, but spectra revealed a surface more akin to an asteroid than a comet. So what was pushing it? The theories ranged from the exotic, outgassing of frozen hydrogen or nitrogen, materials that wouldn't produce a visible coma, to the geometric, that its bizarre, elongated shape, like a cigar or pancake, made it susceptible to radiation pressure from sunlight. The speculation reached its peak when a respected Harvard astronomer published a paper seriously considering the possibility that it was an artificial light sail. The scientific community largely rejected this, but the fact that it was even proposed in a reputable journal tells you how deeply Oumuamua challenged our understanding. It was an anomaly that forced us to consider possibilities we would normally dismiss. The second visitor, 2I Borisov, arrived in August 2019 and was, in almost every way, the antidote to Oumuamua. It looked and acted like a textbook comet. It had a bright, obvious coma and a long, beautiful dust tail. Its spectra showed familiar molecules, carbon monoxide and water vapour. The relief among astronomers was palpable. See, they seemed to say, interstellar objects are normal, they're just comets from other stars. But Borisov had its own quirks. Its carbon monoxide levels were extremely high, far higher than in most solar system comets. Its dust production was chaotic, spiking and plummeting unpredictably, and its nucleus appeared to be fragmenting, shedding pieces as it rounded the sun, suggesting a fragile, weakly bound structure. Borisov was normal, but it was exotically normal. It fit within the known range of comet behaviour, but it pushed the boundaries of that range. Now we have 3I Atlas, and it is not a compromise between its predecessors, it is a synthesis of their strangest traits. Like Oumuamua, Atlas shows features that defy standard models. The 5-point formation, the rapid apparent rotation, the shifting internal structures. But unlike Oumuamua, Atlas is unambiguously active. It has a clear coma, it is throwing off dust and gas. Optically, it behaves as a comet should. Yet like Borisov, it seems to be undergoing dynamic structural changes. The dark ridges, the potential shadowing, the shifting core, all point to a nucleus that is active, evolving, and perhaps even breaking apart. But neither Oumuamua nor Borisov showed anything like the symmetric, coordinated pattern of the 5 points. That is new. That is unique to Atlas. It is the wild card. So what does this trio tell us? One possibility is simple statistics. 3 objects is a pathetically small sample size. If we detect 30 interstellar visitors over the next decade, we will likely find that each one is weird in its own way, and that the weirdness averages out to a broad spectrum of natural phenomena. Elongated asteroids, fragile comets, objects with unusual rotations, all of it explainable by the chaotic processes that form and eject material from planetary systems. Another possibility is selection bias. We only notice the weird ones. Oumuamua was spotted because of its extreme trajectory and acceleration. Borisov was found because it was bright and active. Atlas is being studied because of its anomalous structure. For every one of these, there could be 100 dark, silent, boring interstellar rocks that pass through undetected. We are, by necessity, building a catalogue of the outliers. But the third possibility is the most thrilling, that interstellar space is far more varied than our own solar system. Everything here shares a common origin story, formed from the same molecular cloud, subjected to the same general conditions. Interstellar objects, however, are samples from countless different stellar environments. An object that formed in the hot, violent disk around a massive blue star would be fundamentally different from one that coalesced in the cool, quiet outskirts of a red dwarf system. An object kicked out by a close stellar encounter would have a different history and structure than one that gently drifted away over eons. If this is true, then we should expect every interstellar visitor to surprise us. Not because they are artificial, but because they are showing us the incredible diversity of planetary formation across the galaxy. Theycheck 3i Atlas, then, might be our first sample from a system with extreme tidal forces that create symmetric internal structures. Or it could be a fragment from a larger body that shattered in a collision, and we are seeing the geometric remnants of that fracture. Or its rotation state might have been locked into a complex precession by a past gravitational encounter. All of these are natural explanations. None require intelligence, but all of them push the boundaries of what we thought was possible. Oumuamua taught us that some objects accelerate mysteriously. Borisov taught us that some have extreme compositions. Atlas, if the 5-point formation is confirmed, might teach us that some have geometric properties we've never seen before. Or it might teach us that we are all too easily fooled. But we won't know until we look with the cold, clear eyes of our best telescopes. These three visitors are just the beginning. They are the first 3 sentences in a story that is billions of years old and spans the entire galaxy. While the world's attention was locked on the silent, spinning mystery of 3i Atlas, our own sun decided to stage a cryptic performance of its own. On November 6, 2025, the Deep Space Network's radio telescopes picked up an unusual signal. Solar radio bursts are common. The sun is a constant cacophony of plasma physics, its twisting magnetic fields snapping and reconnecting, accelerating particles that scream across the radio spectrum. Astronomers have classified these emissions into neat categories. Type 3 bursts from fast electron beams, Type 2 from shockwaves of coronal mass ejections. But this burst was an outlier. It began as a typical Type 3 event, a fast drifting sweep from high to low frequency. Then it paused. The frequency drift stopped, stabilized, and for the next 17 minutes it pulsed. Not randomly, but in a pattern that almost resolved into a regular rhythm. The data showed peaks at roughly 3.2-minute intervals, then a shift to 4.1 minutes, then back again. The periodicity was there, but it was slippery, like a rhythm that kept changing tempo just as you locked onto it. Flooring geophysics community divided. One camp argued it was merely multiple, overlapping bursts. Solar activity is the definition of chaos. With dozens of processes happening simultaneously, it's statistically inevitable that sometimes the noise will align to create the illusion of a pattern. Stare at any random data stream long enough, and you will see rhythms that aren't really there. The other camp pointed out that 3 to 4 minute periodicities are real features of the sun. The entire star oscillates like a bell, vibrating at specific modes determined by its internal structure. These solar harmonics can modulate radio emissions, creating quasi-periodic patterns. Not perfectly regular, because the sun is a turbulent ball of plasma, but consistent enough to show up in careful analysis. But what bothered people, what sent a ripple of unease through the community, was the timing. This strange, quasi-repeating burst occurred while 3i Atlas was making its closest approach to the sun, while amateurs were capturing images of geometric patterns, while NASA was in its period of conspicuous silence. Correlation does not imply causation. The sun is indifferent to the passage of a tiny comet. The timing is almost certainly a coincidence. Probably. But here is why it matters for the Atlas mystery. Solar activity is not confined to the sun. The solar wind carries magnetic fields and charged particles outward, creating the heliosphere, the sun's vast cosmic weather system. When those fields fluctuate, when particle density spikes, the space environment around every object in the solar system changes. Comets are particularly sensitive probes of this space weather. Their comas compress, their dust tails shift, and their jets can activate or shut down in response to changing solar wind pressure. If this solar radio burst was a visible symptom of a deeper disturbance in the solar wind, a period of elevated turbulence or magnetic oscillation, then 3I Atlas would have been reacting to it. The 5-point pattern Rye captured might not be a feature of the comet alone, but of the comet interacting with an unusual solar wind structure. Dust could be concentrating at specific distances where incoming solar wind pressure and outgoing cometary gas flow achieve a temporary balance. Plasma structures could form at magnetic field boundaries. We have seen this before. Comet Ison in 2013 showed strange, knotty structures in its coma as it approached the Sun, which were later correlated with solar wind disturbances. The comet was being buffeted by space weather, and its visible appearance changed accordingly. Could the same be true for Atlas? Could the 5 points be transient artifacts of a specific and rare solar weather pattern? It's a compelling possibility, but it doesn't fully explain the symmetry. Solar wind interactions are typically asymmetric, creating a distinct bow shock on the sunward side and a tail pointing directly away. Getting 5 evenly spaced bright points requires either a fantastically specific and symmetric alignment of magnetic structures in the solar wind, which is itself highly unlikely, or, once again, something about the comet itself that organizes its response into a symmetric pattern. The comet's own rotation and vent geometry would be the sculptor, with the solar wind merely providing the raw material. Then there's the periodicity problem. If the solar radio burst is pulsing every 3 to 4 minutes, and the 5 points in Rye's images seem to shift or flicker on a similar timescale, is that a clue or a colossal coincidence? Solar rotation takes 27 days. Large-scale coronal structures sweep past like lighthouse beams. But 3 to 4 minute periods are far too fast for that. They imply localized oscillations, small, specific regions of the corona vibrating like a plucked string. The most likely explanation involves magnetic loops. The Sun's corona is threaded with vast arches of plasma trapped by magnetic fields. These loops can oscillate, with periods ranging from seconds to minutes, depending on their length and the plasma density. If one such loop was oscillating at the right frequency and was oriented toward Earth, we would see its radio emission pulse in time. But why would this affect a comet millions of kilometers away? The radio waves themselves are harmless. They are just light at a long wavelength, passing through space without interacting. Unless the radio burst is not the cause, but a symptom, a visible signature of a broader solar wind disturbance that is simultaneously affecting the oscillating loop and washing over 3I Atlas. In that scenario, the periodicity is a crucial clue. Something in the solar wind is oscillating, creating pressure waves that ripple outward, and both the Sun's radio emission and the comet's coma are responding to the same driving force. Camouflage are now frantically combing through data from the Parker Solar Probe and Solar Orbiter, looking for correlations. Preliminary results show elevated magnetic field variability during the period when RI captured his images. Nothing catastrophic, no major flares or coronal mass ejections, just a period of heightened turbulence, small-scale fluctuations that would normally be considered background noise. But in the context of 3I Atlas, this background noise might be the key that unlocks the mystery. It might be the missing piece that explains why the 5 points appeared when they did, and why RY's timing was, by sheer luck, perfect. Or, the solar activity could be a complete red herring. The universe, with its infinite complexity, could simply be throwing noise into the data at the most confusing possible moment, making it impossible to separate the comet's true signal from the environment's effects. This is the profound frustration of astronomy. You cannot run a controlled experiment. You cannot turn off the Sun's magnetic field to see what the comet does without it. You observe what is there, when it is there, and spend years afterward trying to untangle cause from correlation. The unsettling thought that remains is this: if the Sun can produce quasi-periodic radio bursts that look almost intelligent, then the universe is capable of creating deeply misleading patterns, not just in images, but in the objective data streams we trust most. It reminds us that the line between signal and noise is often blurred, and that the cosmos has a sense of humor that can feel, at times, almost cruel. Gravity is the silent architect of the cosmos, an invisible force that shapes everything from the orbit of a planet to the path of a photon. Yet, for all its power, it is notoriously difficult to measure directly, especially for distant, small objects. You cannot see a gravity field. You can only infer its presence by watching how things move. That is, until now. In May 2025, a research team at the National Institute of Standards and Technology announced a breakthrough that sounds like science fiction: a portable quantum gravimeter. This device, roughly the size of a refrigerator, can detect changes in gravitational field strength with sub-milligal precision, the ability to sense the gravity of an object smaller than a grain of sand. Bribe atom interferometry is not new in principle. It involves using laser pulses to split a cloud of ultra-cold atoms into two wave packets, sending them on slightly different paths, and then bringing them back together. The resulting interference pattern is exquisitely sensitive to any difference in the gravitational field experienced along those two paths. What's revolutionary is the precision and portability. Previous atom interferometers were room-sized, required hours of integration time in vibration-isolated labs, and could only operate in near-perfect conditions. This new device works in minutes, in the field, with an accuracy that begins to approach the fundamental limits imposed by quantum mechanics. Why does this matter for a distant comet? Because gravitational field mapping could utterly transform how we study small bodies in space. Currently, to determine the mass distribution of an asteroid or comet, we must send a spacecraft. The Rosetta mission had to orbit 67P for years to meticulously map its gravity field, revealing a complex, lumpy interior with hidden voids. It was a monumental billion-dollar effort. Now, imagine pointing a quantum gravimeter at 3I Atlas and measuring its gravitational signature, not from orbit, but from Earth. You wouldn't get a detailed map from this distance, but you could detect asymmetries. You could find mass concentrations, dense regions that pull harder than their surroundings. If the 5-point formation is real, if there are 5 distinct objects orbiting the nucleus, a sensitive enough gravimeter would see them. Each object would create its own tiny perturbation in the gravitational field, a wobble that would shift in a precise pattern as they orbited. The signal would be unmistakable. The problem is scale. 3I Atlas is millions of kilometers away. Its total mass is perhaps a few billion tons, a pittance compared to Earth's sextillion tons. Its gravitational pull at this distance is infinitesimal, completely drowned out by the gravity of the Moon, the Sun, even nearby mountains and buildings. But the researchers are already working on the solution: space. The next generation device, planned for deployment on the International Space Station in 2027 and later on a dedicated satellite, will operate free from Earth's overwhelming gravitational noise. In the microgravity environment of space, the sensitivity of such an instrument increases by orders of magnitude. Flooring is where the timing becomes both thrilling and frustrating. The technology is proven, but not yet deployed. By the time a space-based quantum gravimeter is operational, 3I Atlas will be years past its perihelion, a faint, distant speck, too far for detailed study. Unless the mystery proves compelling enough to fast-track a mission. NASA has a rapid response program for targets of opportunity. If the official data release on Atlas shows anything that cannot be easily explained, there could be the political and scientific will to rush a small, dedicated gravimetry satellite into orbit. It wouldn't need to be complex. A single instrument on a fast, simple bus launched within 6 months if priorities aligned. It would point at Atlas, take measurements for a few critical weeks, and answer the question definitively: does the gravity field show the structure of 5 orbiting masses? This is all speculation, of course. The quantum gravimetry breakthrough is, for now, a tool waiting in the toolbox. But its broader implication is profound. For centuries, we have studied the universe almost exclusively with light. Electromagnetic radiation has been our messenger, telling us about surfaces, temperatures, compositions, and motions. But it is blind to what lies beneath. It cannot see the interior structure of an asteroid, the hidden voids in a comet, the mass distribution of a distant star. Gravity does not care about surfaces. It responds to mass, wherever it is. A dense metallic core buried inside a fluffy comet would be invisible to every telescope ever built, but it would shout its presence to a gravimeter. A hollow, fragmented nucleus would have a gravitational signature entirely different from a solid one. This is why planetary scientists are so electrified. Quantum gravimetry offers a new sense, a way to see in the dark. It allows us to peer inside asteroids, comets, and moons for the first time. If 3I Atlas has a hidden structure, if there is something organizing the 5 points or driving the strange rotation, gravity will reveal it. Not with pretty pictures, but with the undeniable language of mass. The conspiracy theorists would undoubtedly have a field day if a gravimeter found 5 distinct gravitational sources orbiting the nucleus. They would claim vindication. But the reality would almost certainly be more mundane, and in its own way more extraordinary. 5 dense fragments of primordial rock and ice, a system of micromoons that formed around another star, a natural configuration so rare we had never seen its like before. Or, the gravimeter would show a smooth, featureless field, and the mystery of the 5 points would collapse, revealed as a complex illusion of light and dust. Either way, we would know. We would have an answer that doesn't depend on arguing over pixels or processing algorithms. The promise of quantum gravimetry is not that it replaces the telescope, but that it gives us a second, independent window onto the universe. And every time we have opened a new window, we have been astonished by what we found. In August 2025, a machine learning algorithm sifting through the immense archival data of the Transiting Exoplanet Survey satellite, TESS, flagged an object that should not exist. A planet, roughly the size of Neptune, orbiting its star with an eccentricity of 0.973. To grasp the sheer insanity of this number, consider our solar system. Earth's orbit is nearly circular, with an eccentricity of 0.017. Mercury, the most eccentric planet here, is only 0.206. Even Pluto, out in the Kuiper belt, only reaches 0.25. An eccentricity of 0.973 describes an orbit that is a hair's breadth from being unbound. It is an ellipse so stretched that the planet's farthest point from its star is nearly 100 times more distant than its closest approach. It spends most of its year in the frozen, dark outer reaches of its system, then screams inward for a brief, scorching close encounter before being flung back out into the deep freeze. The tidal forces during this stellar graze should rip any world apart. The thermal stress from swinging between near absolute zero and star-broiling temperatures should shatter its crust and boil away any atmosphere. Yet the transit data is unambiguous. The planet is there, and it completes this insane rollercoaster ride every 412 Earth days. Astronomers scrambled for explanations. The most plausible is a dramatic 3-body interaction. This planet could share its system with another massive world, a gravitational bully that gives it a kick during each close pass, pumping its orbit to ever greater eccentricities over millions of years. Eventually, one planet is ejected entirely, becoming a rogue planet, while the other is left in an extreme, barely bound orbit. Alternatively, there could be a distant, unseen stellar companion, a brown dwarf or small star, whose periodic gravitational tugs prevent the planet's orbit from circularizing. Or, the system could be the survivor of a stellar catastrophe. The parent star might have had a close encounter with another star, a cosmic near-miss that scrambled the planetary orbits, ejecting some and leaving others, like this one, in orbits that are technically stable, but physically punishing. The profound part of the AI that found it wasn't programmed to look for impossible planets. It was trained on the data of thousands of known exoplanets, learning the patterns of normal transit light curves. Then, it was set loose on the archives to find anything that matched. This planet showed up in its output with a simple, chilling note: high confidence detection, anomalous parameters, recommend verification. Human astronomers did verify it, and the data was solid. The planet was real. It had been hiding in plain sight, in public data for years. No human had found it because no human was specifically looking for an orbit that violated our understanding of planetary physics. This story connects directly to 3I Atlas. The 5-point formation is an outlier. It doesn't fit the standard model of comet behavior. If you trained an AI on thousands of comet images and asked it to classify RISE footage, it would almost certainly flag it as anomalous. But anomalous does not mean impossible. This exoplanet is the proof. It is as anomalous as any astronomical discovery in recent memory, but it exists. Its transits are real. Its orbit is measurable. The fact that our models didn't predict it doesn't make it any less real. It just means our models were incomplete. The same could be true for 3I Atlas. Perhaps interstellar comets can have symmetric jet patterns that solar system comets do not. Perhaps objects from other stellar nurseries develop structures and behaviors we've never seen because they formed under conditions we have never experienced. The exoplanet star is an F-type, hotter and brighter than our Sun. The planet may have formed much farther out and been driven inward by interactions with a more massive protoplanetary disk. Or it could be a captured object, a rogue planet that was gravitationally snared by this star during a close encounter. We don't know, but we accept its existence because the data is compelling. Should we apply the same rigorous data-first logic to 3I Atlas? Should we accept that the 5 points exist in the data, even if we lack a complete explanation? This is the core tension of modern science. Extraordinary claims require extraordinary evidence. An anomalous exoplanet detected by the precise photometry of a space telescope is different from an anomalous pattern in processed amateur images. The quality of evidence is not the same, but both are observations of real phenomena. Both push at the boundaries of our knowledge. The exoplanet discovery highlights the critical importance of edge cases. Most planets have low eccentricities. Most comets have chaotic, asymmetric comas. The bell curve of nature is fat in the middle, but the tails of that curve, the outliers, the 1 in a million objects, extend much, much farther than we usually imagine. There are planets with eccentricities of 0.97. Therefore, there might be comets with 5-fold symmetric jet patterns. These objects are rare, but rare is not the same as non-existent. If we observe 1,000 comets and 999 are typical, we build our models on those 999. When the 1,000th one shows up behaving bizarrely, our first instinct is to assume it's an error, an artifact, a mistake. But sometimes, the 1,000th comet is real. Sometimes, the outlier is the one that teaches us what the typical cases cannot. This is the lesson of edge case cosmology. The rare, the anomalous, the objects that strain the limits of physical law, they are the ones that force us to redraw the maps. They show us the true extent of what is possible. 3I Atlas might be such an edge case, or it might be a normal comet viewed through a funhouse mirror of processing. But the exoplanet discovery should make us deeply cautious about dismissing the strange too quickly. The universe has a long and storied history of producing things we declared impossible. In September 2025, researchers at the National Ignition Facility in California announced a milestone that echoed around the world. They had sustained a net positive nuclear fusion reaction for 32 seconds. This wasn't the fleeting microsecond burst of their earlier breakthroughs. This was 32 full seconds of a self-sustaining star in a bottle, a plasma at 150 million degrees Celsius, 10 times hotter than the core of the Sun, confined by magnetic fields and producing more energy than it consumed. The engineering challenge is almost incomprehensible. Containing such a plasma is like balancing a spinning, superheated tornado on the point of a needle. Any instability, and it touches the wall, and the reaction vanishes in an instant. For 32 seconds, they held it. And when they deliberately shut it down, the data revealed something beautiful and telling. The plasma had not been a formless inferno. It had self-organized. It had formed filaments and bright, coherent structures that rotated around the confinement axis in a pattern that looked, to the eye, almost geometric. Not perfectly regular, but far more ordered than random turbulence had any right to be. This is not surprising to plasma physicists. Hot plasma is the most common state of visible matter in the universe, and it has a mind of its own. Charged particles entwined with magnetic fields naturally form coherent structures. Current sheets, magnetic islands, helical filaments. What looks like chaos on a small scale can resolve into stunning order when you observe the system as a whole. And this is where the connection to 3I Atlas becomes electrifying. The primary criticism of the 5-point formation is that it is too structured to be natural. But if the most turbulent, chaotic environment humans can create, a fusion plasma, spontaneously develops complex geometric patterns, then why couldn't the plasma in a comet's coma do the same? A comet's coma is not environment. It is full of ionized gases and charged dust particles, all moving through the magnetic field of the solar wind. The physics is different in scale and temperature from a fusion reactor, but the fundamental principles are the same. Charged particles and magnetic fields can self-organize. There is a specific plasma instability called the Kelvin-Helmholtz instability that creates remarkably regular patterns. It occurs when two fluids, or plasmas, flow past each other at different velocities. The boundary between them becomes unstable, forming regular, repeating vortices. In space, this has been photographed at the boundaries of planetary magnetospheres, creating strings of bright plasma knots that look, for all the world, like a string of pearls. If 3I Atlas is emitting multiple jets, and those jets are interacting with the flow of the solar wind, you could get Kelvin-Helmholtz vortices forming at the interaction boundaries. From our distant viewpoint, these could appear as bright, evenly spaced points. This explanation requires a specific set of conditions: the right outgassing rate, the right solar wind speed, the right viewing angle, but it is pure, unadulterated physics, not speculation. The fusion breakthrough also serves as a profound lesson in symmetry. The engineers did not design the intricate filaments in the reactor's plasma. They tried to create a smooth, symmetric magnetic confinement bottle. The plasma itself decided to break that symmetry and form its own, more complex order. The structures emerged from the fundamental laws of electromagnetism and fluid dynamics. Nature does this everywhere. Sand dunes form repeating ripples. Cloud streets line up in parallel rows in the sky. The spiral arms of galaxies are density waves, emergent phenomena that look designed but are spontaneous. We see these patterns and we assume a designer. We think someone must have arranged the sand, organized the clouds, built the galaxy. But they are spontaneous. They arise from simple rules playing out on a grand scale until structure emerges from chaos. Is it possible that the 5 points of 3I Atlas fall into this category? Are they an emergent structure, plasma or dust, self-organizing into a symmetric pattern because the physics of the situation demand it? Or are they, once again, just artifacts? The fusion data cannot answer that for our comet, but it does show that the phrase, "too structured to be natural," is often a failure of imagination. Nature is the master of structure, sometimes creating patterns more complex and beautiful than any engineer could devise. Consider the sun's corona again, with its elegant, arching magnetic loops. They look like the steelwork of a vast bridge, but they are formed by the simple principle of magnetic field lines connecting points of opposite polarity. If we discovered the sun today without knowing what it was, those loops would be cited as proof of alien engineering. We would be wrong. This is the trap we are in with 3I Atlas. We are pattern matching, trying to decide if it is too organized. But we do not have a complete catalogue of what natural looks like for interstellar comets. We have a sample size of 3. Maybe 5-fold symmetry is rare, but it occurs when a comet with a specific shape and spin interacts with the solar wind at a specific distance. Maybe we will see it again, and it will become just another entry in the textbook. Or maybe it is unique to Atlas, a 1 in a billion alignment of conditions. The fusion reactor ran for 32 seconds and showed us that plasma can hold complex, ordered structures under the most extreme conditions imaginable. 3I Atlas is a complex system, spinning through space, interacting with magnetic fields and particle flows. Maybe it is showing us structures we didn't anticipate because our models of cometary plasma physics are still in their infancy. Or maybe we are overthinking it, and the points are just hot pixels. But 32 seconds of sustained fusion tells us to keep an open mind. The universe's workshop is full of tools we are only beginning to understand. In January 2025, several months before Rye ever pointed his telescope at 3I Atlas, an amateur astronomer in Australia processed an image of a well-known planetary nebula. These nebulae, the glowing shrouds of dying stars, are common photographic targets. But his processing revealed something startling: a series of dark, concentric rings within the nebula's structure, perfectly circular, evenly spaced. They looked like ripples frozen in time, or the shadow of some immense, structured object. The internet, predictably, exploded. This was it, proof of a Dyson sphere, a megastructure built around the star to harvest its energy. The spacing was too perfect, the circles too clean. Nature doesn't make circles like that, they said. Except it does. Constantly. Within a week, professional astronomers published their analysis. The dark rings were an interference pattern. The dying star had ejected its outer layers in multiple distinct shells during different pulsation phases. Each shell was slightly denser than the surrounding gas. When intense ultraviolet light from the hot stellar remnants shone through these shells, the light diffracted, creating a complex pattern of bright and dark bands in the material behind. A cosmic version of the patterns you see at the bottom of a swimming pool. The perfect circularity was simply a perspective effect. We were looking straight down the axis of a roughly spherical system. If we viewed it from the side, we'd see irregular lobes and messy filaments. The even spacing was a direct result of the star's pulsation period, a natural stellar clock. No intelligence was required, no engineering, just a star doing what dying stars do, viewed from a special angle that made it look impossibly designed. Before that explanation emerged, however, the Dark Ring Nebula was the centre of a media firestorm. It was proof. And the people who believed this were not stupid. They were looking at data that genuinely appeared structured and were asking a logical question. What could make that pattern? Their mistake was not in noticing the pattern, but in stopping their investigation too soon. They saw the symmetry, concluded designer, and did not dig into the library of natural physics that could produce the exact same effect. The instinct to see the pattern was correct. The conclusion was not. This is the final and perhaps most important lesson for the mystery of 3I Atlas. Symmetry is a terrible diagnostic for artificiality. The universe produces symmetric patterns all the time, from the spherical shape of stars and planets to the hexagonal form of snowflakes, from the circular orbits of moons to the spiral arms of galaxies. None of these required an architect. They are the default, energy-minimizing shapes that physical laws produce. Human intuition, honed in a world where neat rows usually indicate a human hand, is a poor guide to the cosmos. So where does this leave us? We need to resist the primal urge to see the 5 points and immediately conclude artificial. The Dark Ring Nebula looked artificial too, until someone did the math. There are natural, if rare, explanations for symmetric patterns in cometary coma. Jets aligned by rotation, plasma structures organized by magnetic fields, dust concentrated by pressure balances or electrical forces. They are not common, but common and possible are not the same thing. What we need is not more speculation, but better data. Not sharpened, stacked and enhanced images, but raw, calibrated observations from the world's best instruments. We need spectra of the bright points to learn their composition. We need time series photometry to track their motion with precision. We need simultaneous observations in infrared, ultraviolet and radio wavelengths. NASA's upcoming data release should provide this. The Hubble Space Telescope has observed Atlas. The James Webb Space Telescope may have as well. Ground-based observatories with powerful adaptive optics have certainly gathered data. When this information becomes public, one of three things will happen. First, the 5 points vanish. The professional images show a normal, lumpy, asymmetric comet. Rise formation was a perfect storm of artifacts, a cautionary tale for the age of digital processing. The mystery dissolves. Second, the 5 points persist, but with a clear, natural explanation. The professional analysis reveals them to be jets or plasma knots or dust clumps, and the symmetric arrangement, while rare, is explicable through a combination of the comet's unique shape, spin, and interaction with the solar wind. Papers are published, models are updated, and the object takes its place in the scientific record as an interesting oddity. Third, the 5 points persist, and no one can explain them. The professional data confirms the pattern. The spectra show unusual compositions. The motion defies standard models. The scientific community is split, and we are faced with the humbling reality that our understanding of interstellar objects, and perhaps of physics itself, is fundamentally incomplete. This third outcome is the one that would change everything. Not because it would prove we are not alone, but because it would prove that we still have so much to learn. The comet doesn't care what we think. It is out there, silent and indifferent, a relic from another star. It holds the answer. Our job is to learn how to listen. The story of 3i Atlas is a reminder that the cosmos is vast, strange, and humbling. Not because it must be full of aliens, but because it is full of physics we haven't yet mastered. Every anomaly is a question, every mystery is a door, and the only way forward is through the patient, rigorous, and awe-inspiring work of science.